Welcome to the course on digital image processing.
In the last class, we have seen the interpolation and resampling operation of images, and we have seen different applications of the interpolation and resampling operations. So, while we have talked about the interpolation and resampling, we have seen that it is the B-spline functions or B-spline interpolation functions of different orders which are mainly used for image interpolation purpose. And before this interpolation, we have also talked about the basic transformation operations, and the transformation operations that we have discussed, those were mainly in the class of geometric transformations. That is, we have talked about the transformation like translation, we have talked about rotation, we have talked about scaling, and we have seen that these are the kind of transformations which are mainly used for coordinate translation. That is, given a point in one coordinate system, we can translate the point or we can represent the point in another coordinate system, where the second coordinate system may be a translated or rotated version of the first coordinate system. We have also talked about another type of transformation, which is perspective transformation, and this perspective transformation is mainly used to find out or to map a point in a three-dimensional world coordinate system to a two-dimensional plane, where this two-dimensional plane is the imaging plane. So, there our purpose was that given a point or the 3D coordinates of a point in a three-dimensional coordinate system, what will be the coordinate of that point on the image plane when it is imaged by a camera. In today's lecture, we will talk about another kind of transformation, which we call as image transformation. So, we will talk about or we will explain the different image transformation operations. Now, before coming to specific transformation operations like say Fourier transform or discrete cosine transform or say discrete cosine transform, before we come to such specific transformations, we will first talk about a unitary transformation, which is a class of transformations or class of unitary transformations, and all the different sort of transformations, that is whether it is discrete Fourier transform or discrete cosine transform or Hadamard transform, all these different transforms are different cases of this class of unitary transformations. Then when we talk about this unitary transformation, we will also explain what is an orthogonal and or orthonormal basis function. So, we will see that what is known as an orthogonal basis function, what is also known as a orthonormal basis function. We will also explain how an arbitrary one dimensional signal can be represented by series summation of orthogonal basis vectors, and we will also explain how an arbitrary image can be represented by a series summation of orthonormal basis images. Now, firstly, let us see that what is the image transformation. You find that in this case we have shown a diagram where the input is an image, and after the image is transformed, we get another image. So, if the size of the input image is n by n, say it is having n number of rows and n number of columns, the transformed image is also of same size, that is of size n by n. And given this transformed image, if we perform the inverse transformation, we get back the original image, that is image of size n by n. Now, if given an image, by applying transformation, we are transforming that to another image of same size, and doing the inverse transformation operation, we get back the original image, then the question naturally comes that what is the use of this transformation. And here you find that after transformation, the second image of same size n by n that we get, that is called the transform coefficient matrix. So, the natural question that arises in this case, that if by transformation I am going to another image and by using inverse transformation I get back the original image, then why do we go for this transformation at all? Now, you will find, and we will also see in our subsequent lectures, that this kind of transformation has got a number of very important applications. One of the application is for pre-processing. In case of image pre-processing of the images, if the image contains noise, then you find or you know that contamination of noise gives rise to high frequency components in the image. So, if by using some sort of unitary transformation we can find out what are the frequency components in the image, then from these frequency coefficients, if we can suppress the high frequency components, then after suppressing the high frequency components, the modified coefficient matrix that you get, if you take the inverse transform of that modified coefficient matrix, then the original image or the reconstructed image that we get, that is a filtered image. So, filtering is very important application where these image transformation techniques can be applied. The other kind of pre-processing techniques we will also see later on, that it is also very useful for image enhancement operation. So, for example, if we have an image which is very blurred, that is the contrast of the image is very poor, then again in the transformation domain or using the transform coefficients, we can do certain operations by which we can enhance the contrast of the image. So, that is what is known as enhancement operation. We will also see that these image transformation operations are very useful for data compression. So, if I have to transmit an image or if I have to store the image on a hard disk, then you can easily think that if I have an image of size 512 by 512 pixels, and if it is a black and white image, every pixel contains 8 bits. If it is a color image, every pixel contains normally 24 bits. So, storing an image, a colored image of size 500 and 512 by 512 pixel size takes huge amount of disk space. So, if by some operation I can compress the space or I can reduce the space required to store the same image, then obviously on a limited disk space I can store more number of images. Similar is the case if I go for transmission of the image or transmission of image sequences or video. In that case, the bandwidth of the channel over which this image or the video has to be transmitted is a bottleneck, which forces us that we must employ some data compression techniques, so that the bandwidth requirement for the transmission of the image or the transmission of the video will be reduced. And we will also see later on that these image transformation techniques is the first step in most of the data compression or image or video compression techniques. These transformation techniques are also very useful for feature extraction operation. By features, I mean that in the images, if I am interested to find out the edges or I am interested to find out the corners of certain shapes, then these transformation techniques, or if I work in the transformation domain, then finding out the edges or finding out the corners of certain objects, that also becomes very convenient. So, these are some of the applications where this image transformation techniques can be used. So, apparently, we have seen that by image transformation I just transform an original image to another image, and by inverse transformation that transformed image can be retransformed to the original image. So, the application of this image transformation operation can be like this, and here I have cited only few of the applications. We will see later that applications of these image transformations are much more than what I have listed here. Now, what is actually done by image transformation? By image transformation, what we do is we try to represent a given image as a series summation of a set of unitary matrices. Now, what is an unitary matrix? A matrix A is said to be an unitary matrix if A inverse or inverse of A is equal to A star transpose, where A star is the complex conjugate of A. So, a matrix A will be called an unitary matrix if the inverse of the matrix is same as, first you take the conjugate of the matrix A, then take its transpose. So, A inverse will be equal to A star transpose, where A star is the complex conjugate of the matrix A, that is complex conjugate of each and every element of matrix A. And these unitary matrices we will call as the basis images. So, the purpose of this image transformation operation is to represent any arbitrary image as a series summation of such unitary matrices or series summation of such basis images. Now, to start with, I will first try to explain with the help of one dimensional signal. So, let us take an arbitrary one dimensional signal. Say I take a signal, say x t. So, I take an arbitrary signal x t, and you see that this is a function of t. So, this x t, the nature of x t can be anything. Say let us take that I have a signal like this x t, which is a function of t. Now, this arbitrary signal x t can be represented as a series summation of a set of orthogonal basis functions. So, I am just taking this as an example in for one dimensional signal, and later on we will extend to two dimension, that is in for the images. So, this arbitrary signal, this one dimensional signal x t, we can represent by the series summation of a set of orthogonal basis functions. Now, the question is, what is orthogonal? By orthogonal, I mean that if I consider a set of real valued continuous functions. So, I consider a set of real valued continuous functions, say a n t, which is equal to set say a 0 t, a 1 t, and so on. Okay. So, this is a set of real valued continuous functions, and this set of real valued continuous functions is said to be orthogonal over an interval say t 0 to t 0 plus t. So, I define that this set of continuous real valued functions will be orthogonal over an interval t 0 to t 0 plus capital T if I take the integration of function say a m t into a n t dt and take the integration of this over the interval capital T, then this integral will be equal to some constant k if m is equal to n, and this will be equal to 0 if m is not equal to n. So, I take two functions a m t and a n t, take the product and integrate the product over interval capital T. So, if this integration is equal to some constant say k when m is equal to n, and this is equal to 0 whenever m is not equal to n. So, if this is true for this set of real valued continuous functions, then this set of real valued continuous functions form an orthogonal set of basis functions. And if the value of this constant k is equal to 1, so if the value of this constant k is equal to 1, then we say that the set is orthonormal. Okay. So, an orthogonal basis function, as we have defined, this non-zero constant k, if this is equal to 1, then we say that it is a orthonormal set of basis functions. Let us just take an example that what do we mean by this. Suppose we take a set like this. So, sin omega t, sin twice omega t and sin 3 omega t. So, this is my set of functions a n t. Okay. Now, if I plot sin omega t over interval t equal to 0 to capital T. Okay. So, this will be like this, and where omega is equal to 2 pi by capital T. So, capital T is the period of this sinusoidal wave. Then if I plot this sin omega t, you will find that sin omega t in the period 0 to capital T is something like this. So, this is t, this is sin omega t, and this is the time period capital T. If I plot twice omega t over this same diagram, sin of twice omega t will be something like this. Okay. So, this is sin of this is sin of twice omega t. Now, if I take the product of sin omega t and sin twice omega t in the interval 0 to capital T, the product will appear something like this. So, you find that in this particular region, both sin twice omega t and sin omega t, they are positive. So, the product will be of this form. In this region, sin omega t is positive, but sin twice omega t is negative. So, the product will be of this form. In this particular region, sin twice omega t is positive, whereas sin omega t is negative. So, the product is going to be like this. This will be of this form, and in this particular region, both sin omega t and sin twice omega t, they are negative. So, the product is going to be positive. So, it will be of this form. Now, if I integrate this, so if I integrate sin of omega t into sin of twice omega t dt over the interval 0 to capital T, this integral is nothing but the area covered by this curve. And if you take this area, you will find that the positive half will be cancelled by the negative half, and this product will come out to be 0. This integration will come out to be 0. Similar is the case if I multiply sin omega t with sin 3 omega t and take the integration. Similar will also be the case if I multiply sin twice omega t with sin 3 omega t and take the integration. So, this particular set, that is sin omega t, sin twice omega t and sin 3 omega t, this particular set is the set of orthogonal basis functions. Now, suppose we have an arbitrary real valued function x t, and this function x t is we consider within the region t 0 less than or equal to t less than or equal to t 0 plus capital T. Now, this function x t can be represented by as a series summation. So, we can write x t as summation C n a n t. So, you remember that a n t is the set of orthogonal basis functions. So, we represent x t as a series summation. So, x t equal to sum of C n a n t, where n varies from 0 to infinity. Then this term C n is called the nth coefficient of expansion. This is called nth coefficient of expansion. Now, the problem is how do we find out or how do we calculate the value of C n. To calculate the value of C n, what we can do is we can multiply both the left hand side and the right hand side by another function from the set of orthogonal basis functions. So, we multiply both sides by function say a m t and take the integration from t equal to 0 to capital T, or take the integration over the interval capital T. So, what we get is we get an integration of this form x t a m t dt integral over capital T. This will be equal to again integral over capital T, and this integral of C n a n t into a m t, because we are multiplying both the left hand side and the right hand side by the function a m t dt, and you take the integral over the interval capital T. Now, if I expand this, you find that if I expand this, this will be of the form C 0 integration over capital T a 0 t into a m t dt plus C 1 integration over the same interval capital T a 1 t into a m t dt plus it will continue like this. We will have one term say C m integral over t a m t into a m t dt plus some more integration terms. Now, as per the definition of the orthogonality that we have said, that a integral of a n t into a m t into dt, that will be equal to some constant k if and only if m is equal to n, and this integral will vanish for all the cases wherever m is not equal to n. So, by using that formula of orthogonality, what we get in this case is we simply get integral x t into a m t dt, this integral over capital T, this will be simply equal to constant k times C m, because the right hand side of this integration that you have said, this right hand side all these terms will be equal to 0, only for this term a m t into a m t dt the value will be equal to k. So, what we get here is integration x t a m t dt is equal to the constant k times C m. So, from this we can easily calculate that the mth coefficient C m will be given by 1 upon k integration x t a m t into dt, where you take the integration over the interval capital T. And obviously, you can find out that if this set is an orthonormal set, not an orthogonal set, in that case value of k is equal to 1. So, we can easily get the mth coefficient C m to be x t c a m t dt, integrate this over the interval t. So, the value of term k will be equal to 1. So, this is how we can get the mth coefficient of expansion of any arbitrary function x t, right. And this computation can be done if the set of basis functions that we are taking, that is the set A n t, is an orthogonal basis function. Now, the set of orthogonal basis functions A n t is said to be complete. We say that this orthogonal basis function is complete if this is complete or closed if one of the two conditions hold. The first condition is there is no signal say x t with integral x square t dt over the interval capital T less than infinity. So, this means the signal with finite energy. So, there does not exist any signal x t with x square t dt less than infinity, such that integral x t a n t dt is equal to 0. This integration has to be taken over the interval capital T for n equal to 0, 1 and so on. And the second condition is that for any piecewise continuous signal x t, so x t is piecewise continuous, and with the same condition of finite energy, that is x square t dt, integral over capital T must be less than infinity. And if there exists an epsilon greater than 0, however small this epsilon is, there exists an n and a finite expansion such that x hat t is equal to C n a n t. Now, n varies from 0 to capital N minus 1, such that integral x t minus x hat t square d t taken over the same interval capital T must be less than epsilon. So, this says that for a piecewise continuous function x t having finite energy, there must be an epsilon which is greater than 0, but very small, and there must be some constant capital N, such that if we can have an expansion that x hat t is equal to summation of C n a n t. Now, this n varies from 0 to capital N minus 1, for which this term x t minus x hat t square d t over integral over capital T, this is less than epsilon. So, you find that this x t is the original signal x t, and x hat t, earlier case we have seen that if we go for infinite expansion, then this x t can be represented exactly. Now, what we are doing is we are going for a truncated expansion. We are not going to take all the infinite number of terms, but we are going to take only capital N number of terms. So, obviously, this x t, it is not being represented exactly, but what we are going to have is an approximate expansion. and if x t is of finite energy, that is integral of x square t dt integration over capital T is less than infinite, then we can say that there must be a finite n, capital N, the number of terms for which the error of the reconstructed signal. So, this x t minus x hat t square dt, this is nothing but the energy of the error signal or the error that is introduced because of this truncation, which must be limited. It must be less than or equal to epsilon, where epsilon is a very, very positive small value. So, we say that the set of orthogonal basis functions a n t is complete or closed if one of these conditions hold, at least one of these conditions hold, that is the first condition or the second condition. So, this says that when we have a complete orthogonal function, then this complete orthogonal function expansion enables representation of x t by a finite set of coefficients, where the finite set of coefficients are c 0, c 1 like this up to c n minus 1. So, this is the finite set of coefficients. So, if we have a complete orthogonal function, set of orthogonal functions, then using this complete set of orthogonal functions. Thank you.